presentation will demonstrate how to get our ULE device into TBR6 mode and measuring RF performance. First step would be to communicate with the device and get it into the TBR6 mode. For this purpose, we would use our interface communication JTAG communication kit, which includes the JTAG adapter board with the USB connection to the PC, and this JTAG connection is inserted into the JTAG plug of the EVB. Next step would be to power up the EVB, the device. We can see here the DECT ULE module, and I'm using an external power supply to the battery jack. I would power it with a 3-volt supply. Once I power it up, I can see current draw of the module, and the next step would be to activate the Vega memory tool, which is the interface GUI for controlling and accessing the device parameter. This is the icon for the Vega memory tool. A very simple installation for this tool, and this is the interface. Once I double click it, I'm using the select target, so the Vega memory tool would recognize the chip, the D6 chip, and now I would like to access the EEPROM. This can be done using the DCC terminal option. Once I select the DCC terminal option, I would like to enter to the factory test mode, factory test menu. This would be by enabling the tabs here and pressing the start DCC button, and we can see now the default factory menu. One of the function of this factory menu would be to write byte to the EEPROM. So we will use this entry number 2, and we would access address of 235 of the EEPROM. This address controls the test mode. By selecting the option 04, we would tell the module to enter to the TBR6 test mode and exit by Q. And now we will have to power it up again, the module. The next power up would be in TBR6 mode. Once we have powered up again the board after the EEPROM configuration, we'll do the select target option again. The DUT is in TBR6 mode. For TBR6 mode, we would use the following setup. So we have our DUT, we have a conducted setup where we connect a coax cable to the antenna port of the module. The module is going to RF mixer throughout a 20 dB attenuator. This is because at Korean band use 1789 megahertz, while the CMD or CTS DECT tester utilizes the Europe band, which is 1888 megahertz. So we need a conversion mixer to interface between these two carrier bands. This mixer is for 95.904 LO signal. The LO signal is used through this signal, a simple signal generator producing an 10 dBm CW signal. Configure the CTS tester. The CTS tester is utilized as a fixed part, meaning it measures a portable part. There is a loopback of traffic going on between the DUT and the tester, meaning uplink and downlink communication. Once we selected portable part for testing, we will press the start button, and then we have to configure the RFPI, the ID of the base, which is the CTS tester. This is a 10 symbol field where we have to configure the one before the last symbol to 1. As you can see here, this is the RFPI which the DUT is configured to receive in TBR6 mode. Beside that, in Korean band, we have 3 carriers that we can work with. It's 6, 7 and 8. So I've selected 7 for the dummy carrier and 7 for the traffic carrier as well. I can choose either 6, 7 or 8 for this purpose. Once the DUT is synced to the dummy carrier, we can see in the power supply that the current is stable, meaning the DUT is locked to the base. If I will go to the home menu, the dummy carrier would not be transmitted anymore. We can see that the device would start searching the base. We can see that by that the current consumption got higher. The device is searching for a dummy. If I will return the dummy again by pressing the start, the device would relock to the dummy, and now we can perform a traffic channel, communication channel, by using the connect button. So now we have a traffic channel going on. We can see it also using a spectrum analyzer. This is a time axis, and we can see here the DECT burst, the transmitted burst of about 400 microseconds and of a power of about 24 dBms. We can see it both on the DECT tester. We have the NTP, the nominal transmitted power, for about 24 dBm. We can see here the deviation performance, about 350 kilohertz, and we can see better the RF modulation. RF modulation is the demodulated signal. We can see the packet pattern, which is comprised of the preamble bits, which is the training sequence, the A field, which is the ID and signaling data, and the B field, which is the actual data. We can measure as well the power time mask and see that it meets the spec of the time mask. We can also measure timing parameters and see that they meet the spec in terms of jitter. And we can also validate the receiver performance by selecting the bare option. We expect the sensitivity level, which means 1000 ppm, 1000 error out of 1 million, come in at about minus 96 dBm or 97 dBm. We can see an average of about 1000 ppm, and we can see that for 0 error we can move up in about 6 dB from sensitivity. We should get 0 ppm, 0 errors, up to the CTS limitation, which is minus 40 dBm. And in terms of transmitted parameter, we measure the following. We measure frequency offset.
Should be less than
50 kilohertz
per slot.
The deviation should be symmetrical, and about 370 kilohertz for figure 31. We call this kind of pattern figure 31 pattern, and the frequency drift should be less than 15 kilohertz per slot. So this is how it should look. In order to change the carrier, we would release the traffic channel, release the barrier, and reconfigure the traffic to be, as I said, 6, 7, or 8. We'll choose 8 this time, and we'll do menu up and connect again to perform a traffic at carrier 8. Now we can see how to measure the occupied bandwidth parameter by the Korean regulatory. We will use a spectrum analyzer for this, and the spectrum is configured to RBW of 10 kilohertz and video bandwidth of 100 kilohertz. The limitation is for 1.728 megahertz at minus 26 dB of offset, and we can see that we meet the spec. We have at minus 26 dB about 750 kilohertz. One side double would be around 1.5 megahertz, so we meet the spec.